So, Kevin, what's the question for today?
Question for today is bond polarity and what in the world does it mean and why is it important?
Okay. All right. I think I can do this one. And I'm going to go back to the photoelectron spectroscopy again. Clearly, I love this stuff, but it's the foundation of everything of almost everything we're going to talk about over the course of the semester. And so, anytime I can relate back to this, I'm going to try and do that. So, we looked at photoelectron spectroscopy data, and if there's nothing else students get from that, it's that different electrons can be removed for different amounts of energy. And so if that's all you got from the photoelectron spectroscopy, we could still move on from there for this part, because what that really says is these elements all have different attractions for electrons. And so this is a table really of ionization energy. It's how much energy does it take to remove an electron. We've talked about electron affinity, which is kind of the opposite, and it goes in the, but every element has a different ability to attract electrons as measured by electron affinity. Bond polarity is really closely related to that. There is a concept called electronegativity. Electronegativity. Okay, and electronegativity basically says that some atoms have more attraction for electrons than others, kind of like electron affinity, but when in a bond, in a shared bond, those atoms will pull, in a bond that shares a couple of electrons, some atoms will attract the electrons towards them more than others, and that's what electronegativity is. So in a shared electron bond, but that, I guess we mean covalent bond, some atoms share more or less, I guess, than others. Let's look at, let me share my screen and go to Cengage for just a second here. So in chapter 8, there's a section called bond polarity, and it has a table of electronegativities. And so, not too surprisingly, the atoms with high electron affinity and high electronegativity are in the same part of the periodic table. Over here on the right-hand side, oxygen, fluorine, chlorine, nitrogen, those are the elements with the highest electronegativity. That means that when nitrogen or oxygen or fluorine or chlorine or sulfur or these elements over here are in a covalent bond with something else, there's a good chance that the pair of electrons that are shared are going to be attracted and spend more of their time near these highly electronegative elements. Likewise, as we move further away down and to the left towards the metals, through the semi-metals, these elements have much lower electronegativity. And you can see the values for oxygen are like 3.5, fluorine 4.0, and nitrogen, or sorry, nickel 1.8, right? So just like electron affinity, just like ionization energy, there are atoms that have a stronger attraction for electrons than others. And we're going to use some of these values to understand bond polarity. You'll notice also, by the way, there are no units on this. These are just relative scales. So that really means that fluorine wants to attract electrons at 4, whereas borine wants to attract them at 2, just means that fluorine's attraction is twice as strong as boron's attraction. Okay?
All right.
So top right-hand side of the periodic table has high electronegativity values. All right, so let's look at some atoms or some molecules. Okay, so here is hydrogen chloride. Hydrogen chloride, depending on how we draw the Lewis structure, depending on what we're showing, here are 2 electrons inside a shared bond between the hydrogen and the chlorine. And if we look at the table of electronegativity values, we'll see that chlorine is 3.0 and hydrogen is 2.1. What that means is that those 2 electrons don't spend all of their time being equally shared. They spend more of their time over towards the chlorine. And so that means that this bond is not equally, that doesn't have equally shared electrons. And so as a result, overall, we would say that this bond is slightly negative at this end, at the chlorine end, and slightly positive at the hydrogen end. And so you'll see, sometimes you'll see these 2 symbols to designate slightly positive and slightly negative. And let me, if you're not familiar with that, you might be familiar with the capital delta, the Greek letter delta, as meaning a big change. So you might do it, look at a change in speed or a change in slope of triangles or something like that, or a change in a graph. But a capital D, capital delta, means a big change. A lowercase d means a small change. Okay, and so you will sometimes see me, and you'll sometimes see in the text, and as you go on further in your career. So you might see a slightly positive change, and you might see a slightly negative change. So slightly positive and slightly negative. I think I wrote slightly. Negative. It's really good you're here, Kevin, to keep track of my mistakes, because I'm clearly capable of making a lot of them. So, so back to the hydrogen chloride. We've got a slightly positive end and a slightly negative end. And so that means that this bond overall between hydrogen and chlorine will be a polar bond. Okay?
Okay.
So let's look at hydrogen attached to nitrogen. Let's go to the table of electronegativities, and we'll see that nitrogen is 3.0, hydrogen is 2.1. So nitrogen is 3.0, hydrogen is 2.1. And so that says there's an electronegativity difference. That means these 2 electrons are pulled slightly towards the nitrogen. They spend more of their time over here. So this bond is polar. And so that means that the nitrogen end is slightly negative and the hydrogen end is slightly positive.
Yep, that looks good.
Yep, and you're occasionally allowed to make a mistake on that, but try not to make it too often. Right? So we have this designation of delta negative and delta positive. Sometimes you'll see me, or you might see other people put a little plus sign down on the end here to show that this is the positive end of that bond. So you might see those sometimes as well. So that's a polar bond for nitrogen and hydrogen.
Okay, so we're talking about polarity and polar bonds. Is there any other type of bonds? Because I think in the text there are other ones too.
Sure. Let's do nitrogen to chlorine. Okay, so let's go look at the table of electronegativity values. And I got to share the screen to do that. Okay, so here's the electronegativities. Here is nitrogen at 3.0, and here is chlorine at 3.0. Ooh, that's a little different than what we had a second ago. So let's stop the share, come back here. So here's nitrogen at 3.0 and chlorine at 3.0. So their electronegativities taken from the table show that, ooh, this pair of electrons between nitrogen and chlorine are equally shared. Both chlorine and nitrogen are pulling them at with the same strength, with the same desires. And so there's not going to be a slightly positive or a slightly negative end. And so if the electronegativity values are the same, we would say it's a non-polar bond. It doesn't have a slightly positive end or a slightly negative end, so it's non-polar. We could do an extension beyond that, which is to say, hey, let's look at oxygen attached to another oxygen. You don't have to look at the periodic table or at that table of electronegativity value. It doesn't matter what it is. I think actually oxygen is 3.5 and oxygen is 3.5. Those two electrons are going to be equally shared. And so there's not going to be any polarity. So this is a non-polar bond. Okay?
Okay.
Which makes me think, if we looked at some that are non-polar and we looked at some that are polar, let's look at some that are super, 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 super polar. Okay?
Mm-hmm.
So if I share the screen here, and we bring up some electronegativity values, hey, let's look at sodium attached to chlorine, sodium chloride. Okay? Sodium is 1.0, chlorine is 3.0. So here is sodium attached to chlorine. Sodium's electronegativity is 1.0, super low. Chlorine's electronegativity is 3.0. So what does that say? It says that the chlorine is really going to be attracting those electrons a lot, right? They're going to be pulled over here. In fact, we would go so far as to say those electrons aren't really even shared at all, that any electrons that are available here are going to spend almost all of their time over on the chlorine. So much so that we would say that chlorine isn't just partially negative, it gets a full negative charge. And sodium isn't partly positive, it doesn't have those electrons at all. And so we'd say it's positively charged. Oh, in fact, what we're really talking about is electrons that aren't shared at all. It's really an electron that's transferred from sodium over to chlorine. And we would more normally write that as sodium chloride, sodium plus ions next to chloride ions. And so if this electronegativity difference is super large, then we would say the electrons aren't shared, they're transferred. And if we have a transfer of electrons, we call that an ionic bond. And it's super, super, super polar, right? I mean, it just goes on and on and on. And so I don't know whether it's 3 supers or 4 supers or 5 supers, something like that. You know, the chlorine is attracting that electron really, really strongly. Sodium is barely holding it onto it at all. And so the electron gets transferred over. So somewhere in there, and some textbooks will say that if the electronegativity difference is greater than 2 or greater than 1.9 or 1.7, depending on where they decide to make the cutoff, they will say, hey, you can have polar bonds, you can have non-polar bonds, but if the difference between the electronegativity values is super large, then you're going to have the transfer of electrons and you'll have an ionic bond. Is that kind of what you wanted me to talk about, Kevin?
Yeah, pretty much. It's
Yeah.
polarity and polar bonds are just kind of an extension of everything we've kind of learned up until this point, with periodic trends, electron affinity, you have a lot of Lewis structures still. And so this is just an extension. And even with this information, we can go further beyond in the course with other chemistry.
Right. Yeah. Bond polarity comes from electronegativity, comes from understanding that atoms want to attract electrons in differing amounts, and that comes from the photoelectron spectroscopy.
Yep. Thank you, Dr. Hunter.
Okay. All right. Thanks, Kevin, very much.